keyboard, and of course, periodic table. And I want to go over writing electronic configurations. So that's why I've got to have periodic table handy. But before we started, I wanted to review all of the different blocks, we call them, on the periodic table, meaning that the blue, light blue here, this is the S block, where the S orbitals are being filled. So any of these elements in this first group, group 1, these are putting the first electron into the S orbital. And group 2, putting the second electron into the S orbital. This block here, which I guess I would describe as a light orange or a salmon color. This is the D block. This yellow over here, this is called the P block. P orbitals getting filled. And down here, the green, this is the F block. Where the F orbitals are being filled. Okay. And also, as a reminder, the S orbitals are filled after just 2 electrons because there is only one orientation of an S orbital. It is spherical. Remind us a little bit what these look like. So because it is a sphere, I could try to do a little bit of shading here, but because it is a sphere, no matter which direction or how you're changing the axes, it will always look like a sphere. Meanwhile, there are 3 orientations of p orbitals. And because each orbital can have 2 electrons, we end up with 2, 4, 6 electrons get filled into the 3 p orbitals. So that's why we have 6 groups that are in the p block. D orbitals, there are 5 orientations. There are 5 different D orbitals. And because each orbital can hold 2 electrons, that means the D block is 10 across. And with the F block, there are 7 orientations of F orbitals. And so that's why it's 14 across. Okay, so just as a reminder, how the periodic table is tied in with the orbitals themselves and the fact that each orbital can hold 2 electrons. So when we are writing our electron configurations, there's a couple different ways you can do it. One is by using the periodic table directly, and another one is a device called the diagonal rule. So let's start out first looking at the periodic table and how we would write an electronic configuration for an element just by using the table itself. Okay, so let's do it for, say, phosphorus. So let's say we have a phosphorus atom. If we look at the rows that we call the periods, okay, they're numbered 1, 2, 3, 4, and so on. So we will always start the left side and with the S block. We know that the s orbitals hold only 2. And as we count across a row, we can count each element as if it were having another electron added. And what I mean when I say that is that even though we're talking about phosphorus, we can count up the electrons in phosphorus, which there should be 15 total, since it is element 15. Okay. We can count up all the electrons by counting along with each one of the elements that come before phosphorus. So this first period here, the s orbital is getting filled. Helium we could actually put here, but the convention is to line it up with the other noble gases because it is stable with 2s electrons, and so we put it where it shares properties with the other noble gases. Okay, 1s2 is filled. Next is 2s. And those are filled here. Okay, then we go over here to the P block. We're still in the second period. There are 6. All these are filled because phosphorus is larger. These are the 2 p orbitals. 2p6. Okay, then we come over here to the third period. We're now filling the 3s. Those are filled. And now jump over to the p block. These are the 3p orbitals. But we're talking about phosphorus. So it's just 3 electrons are in the 3p orbital. And we are done. Okay. What if instead of a phosphorus atom, a neutral phosphorus atom, if we were interested in a phosphorus ion, and specifically the -3, -3 anion. Okay, what does that mean? If it is -3, that means it has gained 3 electrons. Electrons are negatively charged, and we have added 3 electrons to this phosphorus, making it -3. Okay. Phosphorus has 15 protons, so that means that the phosphorus ion, phosphide, has 18 electrons. In other words, it has the same number of electrons as argon, which is quite stable. It's a noble gas, right? Which is what makes the p-3 anion so stable. Okay. So it has gained 3 electrons, and so the electron configuration would be the same, for the most part, as the phosphorus atom until we get to the end. till we get here. Okay. Phosphorus atom was 3p3, but phosphide p minus 3 has gained 3 electrons. So now it is 3p6. Okay. Also, as a reminder, I'm going to pull out my colored chalk. Let's see how these work. Maybe I'll use some of this orange and put orange into blue. Okay. So these are called the core. Core electrons. These are not involved in bonding, or if you're creating ions, gaining electrons, losing electrons, they're not coming from the core electrons, but rather all the bonding, all the chemistry, etc. is happening out here. The valence electrons. My shorthand for electrons. Should put these here too. Okay. All right, I want to do one more example. And this is going to be for one of our what we call transition metals, or D block metals. So why don't we do iron right there, Fe. Okay. So notice how if we were to do iron, this is element 26, we would do a very similar thing to what we did for phosphorus. To start out, we would go with 1s2, 2s2, 2p6, 3s2, 3p6, and then we would come over and fill 4s2. Okay, but then we enter the D block, the D orbitals. And because of the rules of quantum numbers, the very first period of D orbitals, these are 3D orbitals. All right. When you are filling potassium and calcium for S orbitals, these D orbitals are actually higher in energy, so they will not be filled before the 4s. It's kind of a curious thing that happens here. It has to do with something called effective nuclear charge and shielding of electrons. But if you haven't learned about that yet, that's okay, because as long as you know that the very first type of s orbital is 1s, the very first type of p orbital is 2p, the very first type of d orbital is 3d, and the very first type of f orbital is 4f. So if you remember that, 1, 2, 3, 4, it is the 3D orbitals that are getting filled next. Okay. So keeping that in mind, let's write out the electron configuration for iron. Okay. Probably going to have to take 2 rows to do this one time. Okay, let's go. Alright, this is for iron. Let's see how many D electrons get filled for iron. 1, 2, 3, 5, 6. 3d6. Okay, there's our electron configuration for iron. But I wanted to show you one more thing, and that is shorthand notation that you can use, sometimes called Noble Gas Shorthand. It allows you to simplify. I'm going to do it with argon here, because argon is the last noble gas that appears before putting in these valence electrons. So instead of writing out 1s2, 2s2, 2p6, 3s2, 3p6, we acknowledge that that is the electron configuration for argon. So we put argon in brackets, and then we just have to write electron configuration for the valence electrons. 6. Okay, I'm going to put a line here to separate out. This is when we drew it all out, wrote it all out. Here's our shorthand. Okay, see how that works? You always go to the noble gas that is immediately before whatever element you're looking at. You acknowledge that that's filled, and then you just write out the valence electrons. So, some teachers or professors will want you to write out the whole thing. Some of them will tell you that using Noble Gas Shorthand is okay. So just make sure you know what is being asked of you, what you need to do. And either way, you'll be okay, because you know how to write electronic configurations both ways. And you know what are the core electrons. These are the ones that signify the noble gas. Speaking of which, core electrons here, which noble gas does this correspond to? 1s2, 2p2, 2p6. Let's take a look. 1s2, 2s2, 2p6. Right there, neon. Okay, so for phosphorus, we could have used Noble Gas Shorthand notation by putting neon in a bracket and then writing Es2, 3p3. Okay. Well, I hope this was helpful for you, either teaching you a little bit about it or reviewing it with you. going over a little bit of these ideas when you're writing your electron configurations. Thank you for being here with me as always. I so much enjoy doing this for you, with you. And please do let me know what would be helpful for you. I read every single comment and I respond to every single comment that I see. I have, I would say, 99% success in seeing all of the comments and responding. Every so often I accidentally miss one, but I mean to always read them and let you know, give you a response, because I really enjoy hearing from you and either what your questions are or what your kind comments say. It's so much fun doing this, so thank you again for being here, and I will see you again next time.